Alright, so this is tyrosine and this is amino acid. And there are 21 amino acids in the human body. You probably heard of the basic 20 if you've taken bio, was it 275? And so if you're new to chemistry, if you haven't had organic chemistry, you're like, oh my god, what is all these lines? What? I do recognize oxygen, hydrogen, nitrogen, but what's the rest of this geometry? I didn't know this was a geometry class. Well, this is just showing you a skeletal structure of a molecule. So everyone knows this is or hopefully you know, this is carbon dioxide. But another way you can draw carbon dioxide is to take the carbon and then draw the bonds between the carbon and the oxygen molecules. So this is another way of representing the same molecule. And here we have another molecule here. And here we're showing, so this is a cool thing in organic chemistry. When organic chemistry, whenever there's like, you see this angle right here, but there's no atom there, it's implying that there's a carbon there. So we can show the carbon in the central carbon here, but we can also eliminate it altogether in the skeletal structure. So in tyrosine, it actually has all these carbon atoms, but to make this a little less busy and make it easier to draw, they just, whenever there's a carbon at a central as an atom, they just eliminate the C and they just show the bonds. So that's tyrosine. And then there are 21 amino acids. Now, do I expect you to know the structure of these? No, that's more for that cell molecular biology, Bio 275. I don't know if they still teach it that way, but I remember when I took that class way back in the day, we had to draw all the structures and know all these things. I don't expect that for this class. So yeah, don't worry about knowing the exact structures itself. I'll tell you definite general ways to recognize it without knowing any biochemistry or OChem. Now, catecholamines, these are a category, and again, I italicize this because that's more something if you're going to med school, you definitely want to know what they are. If you're going to pharm school, you gotta know what those are. But possibly nursing school, and it might, you take pharmacology, you probably wouldn't need to know that. But catecholamines, what they have in common is that they're made from tyrosine, and this is why I make a big deal about this chemical structure. And then tryptamines, these are made from another amino acid, tryptophan, and tryptophan looks different from tyrosine. Tryptophan is different because it has when I describe it, and I was trying to teach one of my little cousins about this stuff and saying, tyrosine, what shape is this? This is a hexagon, right? There is another hexagonal amino acid with this, what we call a phenyl ring, but tyrosine, I just think of it it's kind of it's kind of roundish looking, right? It's kind of like a tire, so I think of tyrosine has a round structure, a round hexagonal structure like a tire. Tryptophan, it has that hexagon, but it's attached to a pentagon, and if you're taking OChem or biochemistry, this is what we call that indole ring. But tryptophan, it's a hexagon attached to a pentagon. So this is the way I teach it. What's the difference between tyrosine and tryptophan? Tyrosine has that hexagon, and I'm going to think of it pretend there's a car rolling with hexagonal tires for whatever reason. And then tryptophan, this is the one with the hexagon attached to a pentagon. Now, thyroid hormones, and this is why I make a big deal about saying monoamine hormones. Technically, they are made from two tyrosine molecules, but the big difference is when we get to thyroid hormones, they are made from amino acids, but once they become thyroid hormones, they act a lot different. They act way different from these other hormones that are made from amino acids. So again, they consider them thyroid hormones as amino acid derivatives, but I'll cover later on, in a few lectures, why I kind of object to that. So again, mono means one and from one amino acids. And why do I make a big deal about their chemical structure? Well, when you start out with these amino acids and make the hormones that are made from these, this is what we mean by derived. These amino acids, they're chemically changed by enzymes in your body, and they eventually become these other molecules as these enzymes start to change the bonds and add or remove some atoms or add or remove some bonds. So here we have tyrosine, and it becomes dopamine, norepinephrine, and epinephrine. If you were here last semester, that might sound familiar. Here we have tryptophan, and it's going through these multiple steps to become serotonin as well. So back to catecholamines and tyrosine. So notice that these chemical structures are changing as you metabolize tyrosine and change it into these dopamine, norepinephrine, and epinephrine, but something stays the same. Notice that hexagon I made a big deal about, it's staying within all these structures. So in these hormones over here, notice that they all preserve that hexagon, that phenyl ring is kept intact. So this is why I make a big deal about that. If you see just this hexagon and you notice it's a kind of relatively small molecule, it's probably a tyrosine derivative. So all of these hormones, they're actually made from tyrosine. And why do we call it catecholamines? Because this part right here, and hey, we see that hexagon again. This is what we call catechol, but again, this is more, I italicize it because I think it's more for like your advanced classes. Now tryptamines, you also have things like serotonin and melatonin. So they're made from tryptophan, and what do you notice is you have these changes in the structure as we metabolize it, but what stays intact? You notice that hexagon attached to a pentagon, that indole ring stays intact as you make this serotonin here, and melatonin. I should include the melatonin structure next year. But they all keep that same attached indole ring, that hexagon and pentagon attached together. Now you might be like, wait, aren't these neurotransmitters? Like, didn't we talk about epinephrine, norepinephrine being and serotonin like with being neurotransmitters in the brain? And yes, they are neurotransmitters. But the thing about this is that these are the same molecules, but now we're talking about their endocrine roles. So if these molecules are at a synapse, they're neurotransmitters. Because why? They have, remember that the synapse, is that very close association between the axon terminals and the dendrites or cell body of a postsynaptic cell. And then what you have is like these neurotransmitters at a synapse are being directly secreted onto a target cell across the synapse. So you don't really have this like neurotransmitters leaving that synaptic area and diffusing and splashing around to other surrounding cells. It's a very controlled, it's trying to just put the dollop of that neurotransmitter right onto its target cell. Now, if you release a hormone into the bloodstream, remember your blood goes everywhere in your body, right? So now you're releasing it out, it's like sending out a tweet, now it's out into ether and goes everywhere in the world. Same with the bloodstream and hormone. It's a systemic global effect compared to just putting a neurotransmitter directly onto one cell. So I think to think of it as like, think of it like as direct messages versus like a public post. So a neurotransmitter is a directed message, but if you're broadcasting that message all across the globe, that is what the hormones are like, and that's why they're super powerful, because they can be broadcast to potentially every cell in your body. Now, amine hormones, and I'll try to wrap this up. So again, thyroid hormone, I'll get to that later.